This is.
Sì, ma guarda con la chiocciola.
English.
Ah, sì, sì,
Abbiamo il calcio di guida.
Good, good. Right. So I'm just like Professor Yu.
Ci possiamo mai poi. And then back we can try
It takes a few seconds before. Okay.
Hi, Wayne. Welcome. Thank you. Sorry for this misunderstanding.
Oh, that's okay. I forgot to tell you that we use this differently from you guys.
I thought it was like in April, but thank you for being here. Soon we will be starting.
Yeah.
Check if it's still okay.
Can you see the screen?
I can see the screen in your hand.
Not yet.
No, I can see the screen. I can see it. Hey, how are you?
Hi, Paul. I'm Emily.
Yes, how are you?
Yeah, thanks for being here. So, back in Bristol, eh? No, in Amsterdam.
So do you see the screen? Okay. So probably you could mute your part of the Skype. So.
Okay.
Moving, thank you for this final session. My name is Sergio Grosso from Investor Naples, and I would like to coordinate this session for listening the final defense of Mr. Ibrahim. We are five. Two main colleagues are connected by remote, Professor Wemby Yu and Professor Paul Weaver, and here with us is Dr. Pietro Navi and Professor Gaetano Giunta, which will attend this panel session. The candidate, Ibrahim Kalel, has 45 minutes for the presentation, and after that we will start a round of question and dialogue with the member of committees. So please, thank you.
Good morning, or good afternoon, everyone. My name is Ibrahim. So I'm a PhD candidate here with Professor Carrera, and I've been working in collaboration with Dr. Petrolo. So today I'm going to talk about some of the tools we developed as a part of my PhD thesis pertaining to progressive failure and damage analysis of composites. And some of the damage modeling capabilities has been developed in collaboration with Professor Wass's group when he was in Washington. So to give a brief motivation, I think we all are bought into the idea of composites, especially for high performance aircrafts. And as you see here, the latest A350 program has crossed the 50% mark when it comes to usage of composites by weight. And you see over the years, there has been considerable increase in the amount of composites, especially when it comes to primary structures of the aircraft. So current state of the art, it's still very reliant on experimental testing, so which essentially translates to very conservative design approach. And the building block technology which is generally used in aerospace structures, especially when it comes to design, it's still mostly, as you see, reliant on experiments. And one of the reasons could be that people approach designing composites how they approach as metals, essentially trying to translate whatever tools you had from metals for composites, and that could be one of the main reasons for deficiency. So trying to move away from this black aluminum approach, as you see here for the A350 program, they run a simultaneous virtual testing campaign as well. And some of the computational framework which exists right now, or people who are trying to develop right now, includes virtual testing, as we talk here, ICME, digital twin programs. So essentially the idea is not to replace the testing element, but try to supplement in some of the stages of design. So probably this is one of the full-scale testing numerically ever done by a commercial player, as you see here, virtual scale testing of A350 wing. And something I want to emphasize is the degrees of freedom here. It's 60 million degrees of freedom. But even the model still looks quite low fidelity, and if I remember right, they still had just geometric nonlinearity, the material nonlinearity was still not included. So if I could dissect what are the basic challenges when it comes to virtual testing of composites, one is understanding the physics. Most of the experimental campaigns we see here, we still try to see what happens on the surface level. We still don't have an idea what happens inside, especially when we do testing. And the other aspect of virtual testing is building these mathematical frameworks. I think we all are aware of the computational requirement which composite simulation has. So essentially there is a need to build a set of mathematical models which are feasible, especially in terms of early design stages. So the scope of the current research work is to build an efficient, an important aspect, and robust set of numerical tools which essentially can do progressive failure and damage analysis of composite, trying to supplement some of those design levels I showed in the pyramids earlier. So this is how the content of my presentation is going to be. The numerical model we developed is called Carrera Unified Formulation, and essentially we use this formulation to run a bunch of nonlinear analysis, material nonlinear analysis, starting from micromechanical on a lower scale of composite. We do a full concurrent multi-scale analysis, interface modeling with delamination, and finally some of the initial results what we have with respect to impact modeling in composites. So unified formulation. So I'm going to start with the theoretical formulation of it. So the most simplest element you will find in literature when it comes to FEM is a truss element. And if you look at it, all the truss element can do is just takes the axial displacement. That's all the truss element can do. And if you look at the kinematic field of it in a three-dimensional sense, this is how it would look like. So now, when I move from truss to the Mashenko beam, now my finite element not only can take axial tension, but it also can take bending. So essentially what we do, we increase the kinematics. So now with an increased kinematic order, the beam element is able to do more than the truss element. So in a sense, what we do is we kind of refine from truss to beam. We refine the kinematic field. So PUF essentially what it does is supposed to move. Okay. So essentially what PUF does is generalize this entire process where you as a user decide the kind of enrichment you need. And we kind of formulate that in a very compact sense, which is called, we term it as expansion function. So for example, if we want to do Timoshenko beam, the F expansion function would be exactly this. So as a choice of f tau, there are different kinds of basis function you can use. Some of the main work has been based on Taylor series, Lagrange series, and my work would essentially be more based on the Lagrange kind of polynomials. And again, we formulate it within the context of finite element. So all the kind of versatility you get with finite element also applies here. And we formulate in an invariant form. So essentially what that means is you have the same code or the same implementation, and you are able to use it for any higher order models or any kind of materials. So to talk about component-wise modeling, so this is essentially the modeling technique which we employ. So here what we do is we build based on the Lagrange polynomials. So the good part is it's a higher order finite element model, but with only displacement unknowns. And the next part, what we essentially how we model is we take a complex structure. What we have here is reinforced shell structure. We kind of degenerate it into different components, and each component is modeled as a beam. And now just to make sure that the interfaces are taken into account, all the degrees of freedom associated with the interface are made sure it's added up. So that's essentially what component-wise modeling is all about. When you look at how the implementation is, it's essentially generalizing how a layer-wise modeling works. So here I have 3 different layers of composite, and these are the stiffness matrices. So if I have to ever assemble it, this is how it would look like. So essentially what you do, all the stiffness contribution along the interface is added up. So when you look at component-wise modeling, it's essentially generalization of it. Look, here I have a very generic fiber matrix and laminate, similar stiffness contribution, and that's how you assemble. So before I really enter into the nonlinear aspect of our code, I really want to emphasize on the accuracy and basically demonstrate how good or how accurate our models are. So first I'm going to start with a failure index evaluation of a composite, notched composite. We have a notched composite clamped here, displacement is applied on that top. So we are basically evaluating 2 failure indices, Hessian and delamination index. So essentially the idea here is to say how good our stress fields are. So trying to put that into a scalar context. And we compare it with CUF models against Abacus 3D solutions. So what I'm trying to evaluate right now is transverse stress fields through the thickness of the laminate. So first I compare a CUF model where I model each ply with 2 L9 versus Abacus 1 element. And as you see here, the stress fields are quite under-predicted. And there is relevance to this solution here. If you take any damaged or most of the damage modeling or models from the literature, you would see almost everybody uses 1 element per layer for linear brick element, and they are constrained by the fact that it's computationally intensive. And what I really want to emphasize here is the fact that when you try to use 1 element per layer, especially linear element, your transverse results can be really under-predicted. And similarly, the other transfers, as you see here, you get a linear distribution when it comes to Abacus 1 element, but our model, with the kind of computation efficiency we see here, are able to predict those stress fields quite accurately. And if you really look at the failure index field, as you see here, for a given applied load, CUF load tells I'm already going to damage. But Abacus says, no, I'm just at 56%, you can still push further. So basically what Abacus is essentially under-predicting the stress field it should. And essentially what I'm trying to emphasize here is the fact that CUF is not just an alternate way of producing stress, it's also a very efficient way of doing it. And the next result is work we did in collaboration with NASA Glenn, where they were trying to do composite technology explorations. Essentially the idea is they want to check various joint configuration and try to evaluate how different kind of numerical models behave. So we have a configuration here where there is a core composite with taper and essentially in a 3-point bending situation. And this is how we would model. So essentially the beam runs through, and based on the location of the beam element in the structure, we kind of apply different cross section. And essentially this is quite important, given the fact that in the early stages of design, when you're doing sizing, it's very easy to change the configuration here. It's basically just changing one number. And essentially what we are trying to do here is to compare this kind of problem with all the models which was being explored at NASA. So if you look at the results, the peel, adhesive peel stress along this part, you would see we actually capture the stress fields quite accurately for both shear as well as peel. And if you look at the contour stress fields, you would see most of the analytical models which they were trying to explore kind of over predicts quite a lot of stress. And we were actually quite well in comparison with the benchmark solution, where basically the benchmark solution was a very highly dense mesh. So accurate capturing of stress reversals, like I said, and all our analysis was within 2 minutes. So actually you get accuracy in the level of 3D refined solution in a fraction of cost. So before I really enter into composite or nonlinear problems, I just want to emphasize how the the effectiveness of these models has been translated also when it comes to nonlinear modeling of materials. So we take a very simple example, a cantilever beam with a bending load, and basically we apply von Mises plasticity with perfect hardening, and we try to compare different kinds of Cook models, and also we compare it against the analytical model as well as Abaqus 3D film solution. So if you look at the displacement curve, here is the force displacement curve you should get based on analytical solution, and classical models clearly fail because they are not able to produce that kind of stress fields. So now we add Cook solutions to it. It kind of didn't give acceptable accuracy, captures the nonlinear effect, and if I also add the Abaqus result into it, they all capture quite well when you compare with respect to analytical solution. Now I want to focus here on plasticity strength factor. So essentially the idea is to say this is basically the ratio between the load when the yield starts and at the final thing where it plateaus. So you see here our error is well within the limit when it compared with analytical solution, but at a fraction of the computational cost. So essentially, to summarize here is Cook in a way is a very accurate, is able to produce very accurate stress fields at a reduced computational cost, and it is a very powerful candidate for nonlinear modeling of composites. So the capabilities we have developed so far over the last 3 years has been field and mix evaluation, like I talked about, nonlinear models. We did micromechanical analysis, which is currently part of NASMAT, the NASA multi-scale framework. Interface modeling, we also did concurrent multi-scale analysis, and essentially some initial results on impact analysis. So essentially this slide basically condenses 3 years of my work in a way. So to talk about micromechanical analysis, so it's an essential part of virtual testing. So essentially what you're trying to do is you're trying to capture the stress field at a micro scale and components. So there are two key aspects. One is localization. Localization is essentially the fact that you have a macro load, you want to see how the stress field distributions are in the micro scale. And homogenization, essentially you have the stress field at the local scale and you want to know how it the effective compliance of that local model in the upper scale. So there are multiple ways approaches. People start with analytical solutions from Voigt to all the way to semi-analytical formulation based on GMC, and numerical results based on Professor Yu's MSG or even 3D FEM. So if you look at the challenges, still the effectiveness of these models rely on how good your constitutive modeling is, which essentially comes from the experiment. But if you look at the other part of the challenges, you would see its accuracy heavily depends upon what kind of models you use. Analytical models are super fast, but they are only good in an average sense. And numerical models are super slow, but they give you very accurate results. So it's always a balance you have to carry. And this is how we model micromechanical with Cook. Essentially, you take a triply periodic RVE. So we use the same component-wise technique we talked about. Take the RVE, split it into different components, model each component as a beam. And you would see we apply periodic boundary condition to it. And we basically integrate a bunch of nonlinear material models into these RVE, essentially. And we have two sets of material models. One is based on von Mises plasticity, basically trying to emulate shear-driven on inelastic behavior exhibited by matrix using plasticity models. And second one is crack band-based model, where essentially what you do is trying to model explicitly the crack in the matrix. And as you see here, basically the idea is you make sure the energy dissipated by a given element is under this curve, and basic input is generally the energy dissipated as well as the stress at which it starts to crack. And one of the problems when it comes to damage modeling is its spurious dependency on mesh. So what we try to do is we try to scale this curve based on the volume of the element you're considering. So to start with, I have a simple elastic results to start with. Here we have basically take a randomly distributed RVE. These are the fibers and the matrix, and we apply transverse tension. And we try to compute the stress fields. And as you see here, the stress fields we get with our model against abacus compare quite well. But one thing we want to emphasize is the size of the model as well as the time taken. And similarly, we take a periodical cellular structure, we find an RVE for it, discretize it, and we try to compare the Young's modulus. Compares quite well, and even if you look at the stress fields or the stress contours, they are well within the acceptable limit. And now we go a step ahead. What we do is we start introducing nonlinearity, especially using classical plasticity. The essential assumption here is the micro damage or inelastic behavior matrix can be, in a mathematical sense, modeled similar to dislocation in matrix. So another important aspect is our framework is able to take the experimental data. So say you have nanointerpolation data when it comes to matrix, you can use it here. And we try to how do we say, model the nonlinear shear behavior for a bunch of composite material systems, and with a square packed RVE. And as you see here, the results compare quite well with the experiment as well as with the results available in the literature. And to go to the next step, what we take is we take the same randomly distributed RVE and we say the matrix is not elastic, it can also exhibit inelastic plasticity. And we apply the same transverse tension. As you see, the global stress strain curve looks acceptable. And if you also look at the inelastic strains developed within the matrices is also within the acceptable limit. And as you see here, once again, I want to emphasize the degrees of freedom, the number of Gauss points you need, and these values are relevant when you try to go towards multi-scale, because as you see here, essentially what it means is you have a memory efficiency of in the order of 10. And also when it comes to analysis time, we are almost 3.7 times faster. And you would see this when I get into the multi-scale part, this actually translates to much higher savings when we do multi-scale analysis. So the next step what we do is we do micromechanical progressive failure analysis. This is basically the scanning electron image for a composite under transverse tension. As you see here, the matrix starts growing, the matrix starts getting damaged. So essentially our idea is to try to model this behavior. So again, we assume the fiber is elastic and matrix exhibit isotropic fragment. And we have two models with COPE. So essentially the idea here is to show how when you refine the kinematics, how the results are affected. And then to compare, we have 3 different results as well. And if you look here, for a damage analysis, the results are quite acceptable. And if you again look at the global stress fields produced by different models, are within 5-8%, I assume. And again, I emphasize the runtime delay. And here you see how progressively, when I apply the force, the crack starts growing in our COPE model. And essentially each break here translates to the drop you see in the stress. And again, if I compare this damage growth to 3 different models we have at various instances, you see that the growth qualitatively as well as quantitatively compares quite well. So similar result was also undertaken for square packed RV. The results are well within the limit or well within the acceptable accuracy what you see in the literature. And again, the results compare quite well. So if I could summarize, what we started the whole presentation about, the high efficiency is also translated when it comes to handling nonlinearity across scales. And essentially this is an ideal candidate for multi-scale analysis. So essentially that's what we do next. So I'm gonna talk a little bit about what is the current existing theories are and what are the challenges first. So to give an overview, here the idea is, because essentially when you do finite element modeling, you basically apply a material model, and it has basic implicit mathematical formulation. But when you do multi-scale analysis, essentially what you do is you account for the heterogeneity at the lower scale through solving another boundary value problem. And this is important because when it comes to hierarchical structures like composites, localized phenomena heavily influence nonlinear analysis like damage or plasticity, etc. And here there are multiple ways of coupling. Hierarchical coupling is just one way, where say the micro talks to the macro, and or either macro talks to the micro. And sorry. And when it comes to concurrent analysis, there's two-way coupling. So essentially, the macro tells to the micro, this is the load, and the micro tells back to the macro, okay, for the given load, I have the stress and I have the tangent matrix. And synergetic is essentially the blend of these approaches, basically trying to get the good of both worlds. So to look at the literature review, almost all of them, or let's say majority of them, still rely on classical analytical solution, because multi-scale can be really computationally expensive. Like the professor in the last presentation told, it can run for weeks. And people, in some cases, there are also semi-analytical solution, like the ones we see at NASMAT, or even fully FE-based analysis where they do. Also, Lagares and co-workers have developed this global local Latin-based method. And even the commercial software, if you look at it, Digimatch still uses analytical, semi-analytical formulation because of the computational cost. So some way of reducing it is parallel implementation using OpenMPI, or even reduced order modeling using BGD or POD. So challenges again is, if you really want accurate results, you have to have high fidelity modeling at the lower scale. And again, the analysis trade-off, which we always run into when it comes to composite. And also scalability. Even if you take almost all the papers you find in literature, nobody has really done a multi-scale analysis for a full-scale aircraft, and it's still a problem, scalability. So this is an image I took from Professor Baldi's book. So essentially what it says is, as you keep increasing the fidelity, the efficiency drops really low. And most of us still try to be here, because when you have the trade-off between efficiency and fidelity, we always choose the efficiency. So our goal is probably to remain in this part and try to push this ahead to reach the goal as he mentions in his book. So our multi-scale model is concurrent, so there is talking happening at both the way. And here, as an example, as I see, this is my structure. At every material point in my structure, I have a microscale model attached to it, and it kind of talks back and tells this is the stress for the given load you have. And it's parallelly implemented, so we use the hybrid OpenMPI approach, so we can scale it to hundreds of CPUs. And it can handle multiple classes of RDE, like example here, and different material models. And also, since we do implicit analysis, it's important to compute the tangent matrix, and we use the perturbation-based technique to do it. And an important aspect of our implementation is, given the fact that CUF is there in 1D, 2D, and 3D, we made sure the implementation is able to use different combinations of 1D and 2D, just to show how it can be done. And the second part is the fact that how when you use one-dimensional, two-dimensional model, actually I think it's running according to itself, sorry. So matrix computation, like I talked, it's based on perturbation technique developed by Koch and me. Basically what we have is, we have a given macro stress. So basically what we do is we perturb the stress in the 6 direction, 6 normal direction and 6 shear direction. And that's how we compute our tangent matrix. So the only downside to this is, instead of solving just one boundary value problem, at the local scale you have to solve 7 boundary value problems. And since that was the case, we adopted a modified Newton-Raphson method where we compute the tangent matrix only at the beginning of the step. And this is the basic layout of the multi-scale method we did. So essentially the idea here is, macro scale keeps talking to the micro, and micro gives back the stress and tangent field. So I'm going to talk about 3 numerical cases today, 2 based on linear and the final one to exhibit nonlinear analysis. The first one is we try to predict the stiffness of multidirectional laminate. Here basically we have fiber system based on IM7, square factor RVE, and different material layout systems we have, and essentially we compare the results with experimental and literature solution. So this is how we model the open hole. Basically we have a 3-set beam assembly, and we make sure the kinematic congruence are maintained. And essentially at every Gauss point in the macrostructure, we have another micro RV model to it. And if you look at the results, if you compare with experimental results against the solution we get with proof, it's within the 4% of the results, 4% of the value we get with experiments. And the second numerical example is I take the same structure, I kind of interface it with the randomly distributed fiber. And here I have 2 models. So in the first model, basically I use COOF at both the scales. And in the second model, I have COOF in the larger scale and 3D FEM in the local scale. And as you see here, the macro solution compares quite well. It's 3700 in both cases. And now I choose a similar point in both the structure and I dehomogenize, and I get the stress fields. And those compare quite well as well. It's 127 here and 109. So now if you compare the numerical aspects of it, you will see here that the runtime when I compute local field. So essentially what with local field means is once analysis is done at every macro Gauss point, I also find the micro solution. So basically trying to dehomogenize at every point in the structure. And as you see here, the runtimes are actually 4 times faster. And in terms of memory, it's 6 times efficient, let's say. Because the fact that the proof really needs way less number of Gauss points than 3D FEM elements. So now what I do, I take the same structure, I have the RDE, now I introduce plasticity into the mix. So essentially here, it's a nonlinear analysis, but all the nonlinearity is driven purely from the microscale. 2 classes of models, 1D, 1D, where I use COOF at both scales, and I have 3-dimensional model in the upper scale and 1-dimensional model in the lower scale. So as you see here, when I use a coarse 3D configuration, the result is much more stiffer, and as I keep increasing the refinement, my result goes towards the COOF result I get. And if you compare the runtime, it's a difference of 2 hours against 8.5 hours. So there's a real amount of computational efficiency which we talked about in the earlier slide, actually translating when it comes to multi-scale analysis, and also in terms of memory requirement. So as you see here, the nonlinearity is started from here, and essentially you will see the microstructure, it gets accumulated. So almost all the nonlinearity is driven, not almost, all the nonlinearity is driven from the microscale. And if I compare the elastic strain plots for 1D, 1D and 3D, 1D, you will see we have very similar contour plots, but at 1/4 of the time it means. So to summarize, it's efficient concurrent multi-scale framework, and we made sure all the nonlinearity in the local scales are translated back. And on average, we are 3 times faster and 6 times efficient when you compare it with 3D FEM solutions. So the last part of the presentation, the second last part of the presentation today is cohesive modeling. So essentially trying to model delamination in composites. So it's a very predominant failure. We have an example of short beam shear test here, free edge delamination here. And 2 main approaches you see in literature is cohesive zone and virtual crack, and we adopt cohesive zone models. So some of the challenges again with progressive analysis is the computation cost. It's a constant theme running throughout any composite analysis. And also some things is with respect to convergence issues. Since delamination exhibit very highly nonlinear analysis, you specifically need very efficient or very robust numerical method. So what we do is we take the exactly same component-wise modeling aspect and we introduce cohesive kinematics into it. So essentially the idea is you have different bulk elements, and in between bulk element we have this cohesive elements based on COOF. So again, 3 types of elements based on the order of shape functions you use, and we we again formulate it in the invariant format which we talked about in the earlier slide. So these two aspects of our implementation is taken directly from literature. So we take the constitutive modeling based on continuum damage mechanics, the initiation criteria is based on CUI, and the mixed mode law based on Kamani. And in order to make sure our numerical model is able to capture those complex equilibrium path, we implemented an arc length method based on energy constraint. So essentially the idea here is you tell the arc length method in the given increment only dissipate this much of energy. That's it. So the numerical case I have here is quite widely adopted in literature. So essentially it's an experimental study done by Robinson. So you have two initial red cracks as you see here, and we open it. So it's like a mode 1 propagation but with two different cracks happening at the same time, and it exhibits complex equilibrium. So if you look at how we model it, like I said, we model this entire structure as a beam, and based on different location you apply a cross section. So there is one relevant aspect to this which generally people kind of overlook. If you look at it, if you want to do say a DOE or design of experiment, and you want to see, okay, instead of 20 mm, I want to do a 30 mm analysis. So in a traditional sense, if you use 3D FEM, you kind of restart the whole process and you have to remesh the whole thing. But here, basically, what you have to do is just tell this beam element, okay, don't take this cross-section element, take the other cross-section element. So essentially, remeshing in this aspect is as simple as changing one number. So if you look at the aspect of initial sizing, design phase, these kind of tools can be really helpful. And if I compare the results, as you see, the red result is what you get with CUF, and other are the experimental with the black dots, and the two literature solution. Alfano is based on an argument method, and these are based on Ibrahim. And again, what I did was take the CUF results and start from a very coarse 3D FEM model and keep increasing the mesh refinement until it converges towards the CUF. And as you see here, as and when I keep increasing the mesh density, the result tends to go towards CUF. So the aspect I talked about in the initial slides, where I said when you use just one linear element, the stresses are very underpredicted. So that kind of translates to the results here too when you're trying to do delamination propagation. So again, if you compare the numerical aspects, you see analysis time is between 1 hour and 45 minutes against 7 hours. And if you see even the refined result still hasn't captured the kind of results we get with CUF. So this is the propagation you see on the top surface. So there are two different cohesive layers, and it starts with the top surface, it starts in the bottom, and then it kind of coalesces. So the fact that we are able to get accurate stress fields translates to a very efficient as well as accurate delamination analysis. And the next step what we did was, okay, we have essential components of different kinds of modeling. Let's do impact. So here essentially we are in a very initial stage. We are trying to see what kind of models to use, etc. So when it comes to impact, it's computation intensive. I think it's in a completely different league. When you talk about intensive, it can run for probably weeks. And complexity arises from multiple places. You have contact detection problem, discretization problem, how to enforce the contact, and also the solver, because you really need a very robust solver when it comes to modeling contacts. So, and only literature, at least so far, we could find based on 1D models was done by Zavarisi and Riggers, where they used Euler-Bernoulli or Timoshenko beams. So what we try to do is formulate the same problem within the CUF formulation, the invariant formulation which we talked about. And we are trying to, how do you say, explore different various forms of doing it, because it's not done in the literature in the past with higher order models. So you see, we're trying to describe it node to node, node to surface. We're also seeing how to enforce the penalty and also how to have different kinds of solvers. And I'm going to show two numerical results today. One is rectangular block and one is broad impact. And if you see, basically what I have here is a smaller cube impacting a larger cube, both modeled using CUF. And if you see okay, the initial impact, the stress rate propagates and it kind of bounces back. And similarly, what I have for rod impact is two rods being impacted. And if you look at the results, this is the displacement at this point, and as you see, there is an initial compression, a bounce back, and then it goes to 0. And here we are trying to basically impact with our models. So to finalize, the initial assessment affirms the applicability of proof even for impact modeling. So the outcome, we developed a computationally efficient nonlinear tool for composites, and we are able to capture various modes of nonlinear phenomena across scales, starting with progressive failure, relamination, creeping nonlinearity, etc. And the testing framework we have shows multifold efficiency, not just in terms of degrees of freedom, but actually in terms of the memory it uses, the time it takes. And it's scalable as well. And during the part of my work, I have also developed a bunch of in-house GUI so that people can, or with Abacus, so that there is, people can use it even outside our group, let's say. To summarize, this is the pyramid I talked about. We developed mechanics and mesoscale modeling, which could supplement these two pyramids at 3 times and memory 5 times. And I have multi-scale modeling, which could actually supplement these two pyramids. And we have a savings of 3 in terms of runtime and memory in terms of 6, and interface and impact modeling, which could be used in all these 3 blocks we talk about. So this is essentially what I took from Professor De Rosa's review, where essentially when it comes to composite, what he mentioned in the review was it's very different to draw a line where the design of material ends and where the design of structure begins. And when you could, how do you say, join the aspect that you could not just use computational models and constitutive modeling, but also theory of structures into when you are trying to model the problem, it can really translate into quite a bit of computational efficiency for different kinds of problems you have. So publications so far, 12 in terms of journal publication, a chapter in a book under Fullcom, conference proceedings. I would like to thank Professor Yu, Professor Was, Mr. Kapilani, and also Dr. Pineda for hosting me throughout these 3 years of different instances. And last but not the least, Fullcom for being very generous when it comes to funding our research project, and also HPC from Polito, who were very enthusiastic to give us as many CPU cores as we wanted. Thank you.
Thank you, Ibrahim. First of all, I have to express my congratulations for the way in which the thesis is written. And I have always remarked about your speed in speaking, because you are extremely fast.
Yes.
And also the new foil are very dense. This is always a remark for your future. I hope that you will reduce the speed in your career. After this, I would like to invite the colleague to start with a round of questions. Probably, Professor, you can start the discussion.
Yes.
Can you hear me?
Yes, Professor.
Okay, good. Abraham, first I would like to congratulate you that did a great work, and that's really impressive. You not only take advantage of the efficient accurate calculation from the curve framework, and also touch so many nonlinear behavior and difficult problem of composites. So I'm really impressed by that. And I do have a few questions for you. Make sure that I understand what you're presenting. First, let me say we can go from the end maybe.
Okay.
And first, I would ask, when you say you integrate with abacus, what kind of integration you're talking about? Because the curve elements are very, very different from abacus elements.
Yeah, essentially the aspect we're talking right now about is pre and post processing.
Oh, okay,
So,
okay, I understand that part.
Yeah, so
Okay, good.
we use Abacus as a front end to generate the inputs, and we
Okay.
use our executable to run the analysis, and then we again use the Abacus to post process or generate ODBs for
Okay.
post processing. So
Okay, good. And on your summary slides, you basically say that this work you enabled basically could have a runtime say up to 4
Right.
times faster, memory up to 6.
Right.
And people may argue that this may be not a strong motivation enough for them to move from one familiar code. For example, if you're talking about the impact,
Right.
then they will use ALS data, say they were 4 times faster. I will buy 4 computers. How do you basically sell your message to you guys like this?
Right. I mean, another important aspect again here is it's not an optimized code. We are still more how do you say, emphasizing on the fact that to get the physics correct and to make the codes faster. So probably I think there is still a lot of room to make the code faster in terms of implementation. I mean, sometimes we change from a 2D array to 1D array to save matrices, and it speeds up the code by 3-4 times. And it's not something which we keep implicitly in our mind. So I think probably if we could spend a certain amount of effort to optimize it, I think we can see much higher, how do you say, efficiency we are talking about here. Because when you look at the mathematics of it, it's there. It's just that we have to translate the kind of equations into a very efficient implementation, let's say.
Okay, good. Okay, another question is more general, that the people think that being composers,
right,
this failure and the progress failure analysis and all that,
right,
the more important problem is the model itself, the constituent model. You show the slides,
right,
structure series
right,
and computational model, and then constituent models.
right,
Really, it's the, say Hashin.
right.
Why use Hashin? Or J2 plasticity. Why use J2 plasticity? How do you determine numbers? For example, that for cohesive loop model, people say, oh, you're talking about mode 2, mode 3, and mode 1, and even mixed mode.
Right.
But that are not necessarily good models to model your structure. How do you answer that question, or have you thought about that?
Right, I mean, even in the initial slides, I talked about this whole 2 challenges when it comes to virtual testing, and one is exactly what you just mentioned. So I think in a lot of ways, you got to supplement the kind of numerical modeling we do with experimental data. And probably some of the reasons why we still use Polymerase plasticity is because it's easily available.
Okay,
So,
good. So you haven't really do anything related with that part?
No. Most of the work has been computation. We are trying to see we took the concept of what people do, and we kind of implemented that into our framework and tried to see how we get the efficiency, let's say. Okay.
On your slide 3, you borrowed a picture from Jacob body. I think that that diagram is a little bit confusing, particularly in view of what you're doing in your look. It basically implies that if the model is more accurate, then it must be more expensive, which you basically, and your work definitely basically shows the contrary. You not necessarily need the high expense to get a high fidelity.
Right. I think at least you're talking about which slide again? 3.
There's 31.
31.
That's 31.
Yeah, from Professor Baldi, yes. I think the aspect they have put, or at least the data points they have, is based on the current state of the art, if I'm right.
Yeah, you maybe need to put something, say you put the curve somewhere, this on the, let me say the right and top,
Right, close to goal, let's say.
This
Maybe even above goal if things work.
And also when you do modern scale modeling, you're talking about all the aggregate space, but there's a scale separation.
Right.
Basically, at each Gaussian point, you take R and E out.
Right.
Then you imply the periodic boundary condition, but in reality, those boundary conditions are not periodic.
Right.
You handle this artificial discontinuity basically created by this RE analysis.
Right, I mean the aspect that there is a scale difference, because for example when you try to do let's say sandwich with hexagon, I think you can really see the scale difference aspect there, because there is not much difference from the structural scale you're trying to analyze versus the sandwich core you're trying to kind of homogenize. At least my current assumption here was the fact that with composites, we are talking at fiber which is in the range of 7 to 10 micrometer, or let's say 10 cross 10 micrometer, and the structure we are dealing with is in at least a couple of centimeters or even meters, let's say. So I thought at least there is a clear scale separation when it comes to fiber reinforced composite. And if you, I mean, there are also, I think, let's say when you have the Gauss points close to the boundary of the structure, where the periodicity is not valid anymore. So I think in such cases, probably it's not implemented yet, but I think you also find in literature where they try to relax the periodicity. Like in terms of textiles, they relax the periodicity in the Z direction. So probably something of that sort could be done, I assume.
Yeah, Ibrahim, what I ask the question may be slightly different. I mean that even you have, this traditional unidirectional fiber reinforced, we all know that fiber is much smaller than the layer thickness and all that.
Right.
But the scale separation is still only valid for global behavior, not for the local behavior. When you go to basically study failure and damage, basically you're looking at the local behavior.
Right.
There is some called multi-scale finite element method.
Mm-hmm.
They try to handle so that basically, because at the boundary, we really, no matter what it is, because you have zoom in to see the space concentration and all that.
Right.
That RV analysis really creates the artificial discontinuity there.
Right. Okay.
And another question is that on slide 36, you have this, it looks like to me the dehomogenization takes 3 times or 4 times more than the homogenization, right? Because without local fields, you're talking about 3 seconds. Then with the local fields, when you want to do dehomogenization, it's 10 seconds.
Right.
What happens there?
Yeah, actually, without local fields is basically only homogenization happens. So I start homogenizing this and applying the C to every Gauss points here, but I don't dehomogenize. But in the next
Why
case,
dehomogenization takes so long? I don't know whether, I think I taught you MSG, right? When we do dehomogenization, it's almost zero cost. There is no cost with dehomogenization. You already calculate all the fluctuations and all that.
right. No, but I think here it's the fact that there is quite a big number of Gauss points, probably running in the order of 20 or 30,000 Gauss points. So, and it's not done parallel, it's done linearly, right? So even if it's few microseconds per Gauss point, you multiply that with the number of Gauss points, so probably that could be the reason. But essentially it's the same, since it's linear elastic, we just solve the micromechanical problem only once, so we are not solving it every time for the dehomogenization.
Okay, so you use the parallel for the homogenization, not parallel for the dehomogenization. So that is not clear from this table, so that's why I get confused.
Right. I mean, because parallelization is done in a very global sense, so locally we haven't done any kind of parallelization yet.
Okay, then I think I used more time than I have been allowed. Then I have one more question. When you do the failure index, you compare the say because the one linear element, 4 linear element, then compared with layer-wise 2. Layer-wise 2 is second order layer-wise?
It's how do you say, piecewise second order. So every ply has, how do you say, piecewise quadratic expansion per ply, let's say.
Okay, so then that is not fair compared with the linear element. Because the linear element, no matter what you do, you have a piecewise line there.
Right.
I suggest you put, say, abacus one quadratic element.
Actually, in the paper, it is there. I haven't just put it here. I mean, essentially, my point there was to emphasize the fact that people still use linear element to do it, and to say that the stress fields are really under-predicted. So, I mean, you can put delamination element with one linear element and make it supposedly increase the fidelity of your model, but the input to your delamination element is still highly under-predicted. So that was the case I was trying to make there, essentially.
So have you checked that really for this, when you do the delamination, phase index stuff, they basically talking about this interlaminar transverse shear stress.
Right.
How many elements per layer you need to get the shear stress converge?
I think we had done it for unnotched laminate, if I'm not wrong, for a biased mesh density. I mean, making sure the mesh density is biased towards the client interface. It was up to 6, if I'm correct. 6 to 7.
Yeah. If you want the stress results, usually quadratic elements, its beta, of course, is more expensive.
Right.
We know that.
Right. I think in the paper we did compare it against the quadratic as well. So, yeah.
Okay. At one slide, you had the comparison with FGMC and HFGMC.
Right.
About the results, have you also compared the time?
No, actually, in the reference paper I was checking with, they just had the plots, not the time.
Okay, but you stayed at NASA, right? You have the code.
I mean, not personally with me, but I think probably we could try in the future and see how that. I mean, we are trying to do that right now, trying to do the time comparisons with our code versus their code.
Yeah, because one of my students did some comparison with GMC. We found out for some cases we can even be faster than GMC, and of course with much better results. I believe this year will be the same case with the curve.
Right. Yeah. I think right now we have placed ourselves in the fully numerical method under the NASMAT. So I think in the coming days we will do we are planning to write a report dynamics with Cope as well.
Yeah, I think that I've done most of my question, and one more question maybe not only for you and also for Professor Corella, is that basically, I mean, based on curve, you have to pretty much redevelop the whole system.
Right.
Then how do you convince others to abandon the existing, FDM and XFDM and to use curve-based simulation framework?
Yeah, so Wemby, we are not trying to convince them. We hope they will be convinced by their own themselves about that, if it's the case. We don't do this work, yes. We just make our work running, and then we see what is going to happen.
I think.
Yeah, but you're right. Probably you have to try. I don't know. Business of that. But we should learn from you how to do it. Yeah, but you are right. Yes, we need probably to do a little bit of work in this direction.
Yeah. I mean, at the end of the day, you have fantastic tools. You want somebody else to use, but they have to basically say, choose one or the other because it's not both, right? They are necessary.
Yeah, but what is the experience I have now, that there are really few people that know finite element, and many people that are using abacus and ANSYS. So they know that they have a tool to run, to solve problems, but they don't know that they are using finite element. So how you can convince them that there is possibility to have another framework, finite element framework, because they don't know what is finite element.
Around, and then you say, oh, that's the same tool, both sides looks the same, right? I'm done with my questions. Ibrahim, again, and congratulating you.
Thank you.
Great work. And what's your future? You're going to be a professor somewhere?
I think for now I'm going to continue here and let's see what's next. So for now I'm going to continue working with Professor Karela.
Yeah, okay, I will let him free. No problem.
Thank you, Professor Yu. Now.
Okay. I need to leave now because my family is still waiting for me to take them to the capital. Capital to visit.
Okay, thank you.
Thank you, Professor.
Thank you. We got a note of your comments, so we'll take care of it. Okay, thank you, Wendy. Have a nice day.
If there are any other paperwork I need to do, let me know. Just send me email.
Yeah, I will contact by.
And also, US congratulating you on a great student. You did a great advice, and it's quite an accomplishment.
Thank you very much.
Thank you.
All
Now,
right.
Bye-bye.
Professor Wheeler, is your time for questions.
Okay, well, how do I follow that? Fantastic work, Ibrahim. I'm extremely impressed by the quantity and quality of what you produced in just 3 years, and a phenomenal communication as well with the outputs.
Thank you.
So I wasn't going to concentrate on your presentation, but go back to the thesis, which I made a few comments on. But just as a philosophical point, I mean, I'm a fan of CUP anyway, as you know from FullComp with the team been utilising it, and we're finding things we were able to do with it we weren't sure it could.
Right.
When you're doing high order expansions through the cross section, when you've got low order expansions along the beam,
Right.
okay. Then as we go back to Ritz's method, where basically you can use any polynomial representation as long as it's complete polynomial and linearly independent. If we expand our polynomials from the cross section with the beam axis, we don't have complete polynomials because we have higher order polynomials through the cross section than as we do along the beam.
Mm-hmm.
So I wondered what your thoughts were on the benefits and limitations of this incompleteness in the polynomials that are used.
How would you define the incompleteness? I didn't get that fact.
Okay, so for example, in the cross section, let's call the cross section y and z. So if we had maybe we have fourth order polynomials in y and z.
Right.
Okay,
Right.
and then actually along the beam we only have quadratic.
Right.
If you expand them all out,
Right.
you're going to have some x4, y4, x squared, y4, z4. So that's the 10th order polynomial, but that's the only one that exists. It's not complete to the 10th order, is it?
Right.
So do you see what I mean?
Right. I mean, if you look at the, how do you say it, the intention of what you're using it for, given the fact that, say, you have a problem in hand where the how do you say, the output of it, what you're expecting is purely based on the cross-sectional deformation, let's say, right? And you're not really concerned about the axial deformation or whatever happens through the axis. So
Yeah,
I think
you're right. I agree with that.
right. So in a way, I think it's also, as a user, you get to choose instead of putting choosing an order and putting it all over the structure. CUF in a way gives a very compact and concise way to concentrate on the certain aspect of the structure, right?
But if you use, I just wondered, have you, because you've done a lot of material nonlinearity, you've done an awful lot of very complex, difficult problems.
Right.
Did you, how much numerical conditioning did you observe in the process of this?
Yeah, for Taylor-based, yes. When we try to do Taylor-based polynomials, essentially, there again, if you look at the fact that, let's say the value x raised to 4, and if you compare that degrees of freedom with x raised to 1, the ratio is quite drastic. And as you pull much further, the condition number gets skewed. And when you start introducing non-linearity into it, I think it kind of skews it much further. So let's say we generally hit a ceiling when we try to do Taylor series at the order of 7 or 8, the condition number gets really bad. Depends upon the problem. And if you have a similar problem and if you put plasticity into it, I think you kind of hit the ceiling quite early.
Okay. It makes sense. It made me think whether you could almost use this approach to define what it means to be a being, actually.
Right.
Because as you say, you quite rightly say, I agree with you, but for the approach to work, if you're going to have rapidly varying variables, they have to happen in the cross section.
Right.
through the cross section, not along the axis.
Right.
Right. So there's probably a mathematical definition for a beam that we could, or you could define here, which I think is kind of interesting from a philosophical point of view. If, for example, if you've got a non-educated user of cuff, they could put the wrong expansions, get ill conditioning, where an educated user would not, for example.
Right.
You're a highly educated user, and you've done phenomenal things. But I just, I'm still personally concerned that when we use, we are not sure a priori what the variation differences will be between cross-section and beam. So I want to ask again, as you were experimenting and developing these models, did you have to, you said Taylor didn't work so well, so you used Lagrange binomials, but did you find to get your expansions to converge, or not really?
I think your voice was breaking. Can you repeat the last part of your question?
Yeah, I just want to know whether, when you were getting your models to work,
Right.
you always could determine a priori the order of polynomials you needed to get convergence, or did you have to do trial and error sometimes to avoid ill conditioning?
No, I think in most cases we do trial and error. So we kind of generally the process, at least I adopt, is to start with the conventional way of how we model, like the intuition way of what you feel, and then kind of go a little up and go a little down in terms of mesh density, and try to find the optimal path. It's mostly, how do you say, intuitive driven than.
I think it's a little unfair. I think it's less intuitive because I think there is more rigor to it than
Yeah, sure, of course, yeah.
Actually, I think the fact that we're not using complete polynomials to the same order as the cross-sectional expansion is the reason for the, obviously for the computational efficiencies,
Right.
as opposed to commercial 3D-FD. So it's something that Cuff exploits in a very positive way, actually.
Right.
It's just knowing the bounds of validity a priori, whether that is possible. That's all.
Right.
So yeah, thanks for that discussion. I've got some questions about some of the models that you ran. So if you look at your thesis, section 232, and you've got the notched hull, I showed some of the results in your slides, I think, early on.
Right. For the failure index?
I didn't hear you there, sorry.
For the failure index? You're talking
Yeah, just before that, I mean, if we're looking at, I've got your thesis, and if I look at figure 219, for example.
Unfortunately, I don't have. Oh, yeah, I do. Sorry. Section?
It's 232. I think the thesis page is 39.
Okay, yeah, sure.
So, your conclusions.
Right.
A little concern you're saying if I look, the penultimate sentence of your conclusions, which is page 41, is sort of referring to those results. It says the inability of standard 3D-FM to capture for plane stresses.
Yes.
That's quite a claim. I mean, if you just refine your mesh, are you telling me even with 3D-FE, commercial FE, you will not converge to the appropriate results in all cases if you use a dense enough mesh?
Yeah, probably I think I missed out a word called standard process of using 3D film. Probably it's much more, how do you say, lesser of a claim. Essentially, my idea there, I would say, is the fact I have reiterated throughout the presentation. The fact that when people tend to use 3D fem linear element the way they use it for metals, and kind of overestimating the capacity of these elements to produce results. Is essentially what I was trying to highlight. But I think, yeah, that's probably a wrong way to formulate that statement. Yes,
in my experience, in the team that do these sort of works, they'll never use this one element for there and that. So I think, I'm sure that's appropriate comment.
Right. My whole idea here is, again, if you take any damage modeling papers for composites available in the literature, over 80% or let's say 70% of the people still use linear elements, and most of them still use one element through the thickness.
one element still?
Yes.
Oh gosh, wow, okay.
And they still put delamination elements between these linear 1D elements. So
Okay.
I think we are trying to make that point essentially.
Yeah, and you make it very strongly. I'd say it's see one kind example. Well, I guess we want to know there's no experimental results, obviously, here.
No.
You can't get full-built interior stresses yet. Not so easily, anyway. But how do you know that if I look at 219, but you're basically saying that cup LW2 is the most accurate solution?
No.
How do we know that?
The idea here is we fundamentally assume it's the most accurate of the models you have, and the reason why we say that is as and when we keep increasing the mesh density with 3D element, the results kind of tends or starts to converge towards the result what we get with LW2. So it's the initial assumption that it's the most accurate, and the convergence results we get with 3D kind of tries to prove the hypothesis, let's say.
Okay, so let me just have a look at that. So at that point, that's so we look at which is the most accurate there of your abacus models. That's your 3D 2LQ. What does the 2LQ stand for again, please?
It's 2 elements per ply and quadratic brick element.
Yeah, 2 quadratic bricks per layer, is that right?
Yes.
Oh, wow, okay. And so let's have a look at that surface, at the free edge. So the traction-free edge of the notch, or the hole. It's really a hole, isn't it?
Right, yeah, it's a hole, yeah.
Yeah, it's a notch. So explain how those stress-free boundary conditions are actually satisfied, please, compared to... Because are you extrapolating from Gauss points here? How are you doing that?
No, not really. That's also another aspect which we like to highlight. When it comes to commercial software, they kind of interpolate between the Gauss points when they jump between elements. But what we do is we kind of use the exact strain displacement relations in a given element. And for a given node in an element, we use that strain displacement to compute the strains and consecutively the stresses. So there is no interpolation as such. It's almost zero.
Right, okay. I also was going to say that I would have expected, I was trying to get some physical insight from the stress distribution,
Right.
and I would have expected, I was just trying to work out which way the Z was and where the top and bottom stuff, but I guess when Z is 0, that is if I look at 218, where there's well, actually no. You explain to me where Z is 0, where Z is 0.5, please.
It should be from for figure 2.19.
Yeah.
Z0 should be from the top to bottom, if I'm not wrong. Should be from top to bottom.
So the top surface.
Yeah, so it's 0 degrees on the top, in the middle 2 is 90, and then I have the 0 at the end.
Oh, no, I didn't mean that. I just meant Z coordinates. Where is Z, the value in millimeters equal to 0?
It's the on the topmost surface.
Okay, all right, okay. That's fine. So actually, when Z is what's the midpoint, the middle layer, the mid position? Is that 0.25? Is it
Not essentially. I think the thickness was. I have to check, but I don't think it's exactly 0.5. So it should be somewhere between 2.2 or 2.3, I assume.
The middle, okay.
Yeah.
The reason what I'm saying is actually, where is it, the value of Z where you hit the free surface of the hole? What's the value of Z there?
Free surface of the hole.
Yeah.
It's at the Z equal to 0 at the end. So essentially I have the stress through. The Z is perpendicular to the open hole, what you're seeing.
That's right. So I'm just trying to say I would expect sigma YY
Right.
at the hole to be 0. Is that right or not?
Sigma YY.
Yeah, at the hole to be 0. It's stress free.
Okay. Oh, I don't see here. So again, you're saying in the stress free. Yeah, that's true.
Actually, sorry. Wait. Let's be a little bit careful here. I'm going to get my coordinate system right. So is sigma y
Right.
in the through thickness direction, or is it in the plane across the width of the beam?
It's through the sigma.
It's through the width, isn't it?
Yes.
Okay. So I would expect sigma yy, where you have the dot,
Right.
the red dot,
Yes.
to be 0 at that point because it's stress free.
Oh,
Am I right?
I have to check. I think it's going to be sigma y. Through the thickness, this should be y.
Yeah, just take your time. I'm just trying to understand the physics. So I'm looking at figure 2.18.
Right. So you're saying through the thickness at the free surface it has to be 0. That's what you're.
Oh, wait a minute. Wait, sorry. I'm saying that sigma yy at the free surface
Right.
should be 0 at that red dot. I'm trying to see why, if you look at 2.18,
Right.
okay, Z is into the plane of the figure. So we can't see the Z coordinate. The length coordinate, width, is that correct?
The length coordinate is y.
The length is Y.
Right.
Right, okay.
I think it's showing up the coordinate because the smaller dimension is x, the longer dimension is y, and z is perpendicular to the book or to the image.
Right, okay.
Yeah.
So what about, did you calculate sigma, oh, you have got sigma, so sigma xx, did you calculate that?
Oh, I think we did, but probably I haven't plotted it here.
Okay, but then I look at the other things, sigma xy
Right.
should be 0 on that surface at that red dot, which will be in figure 219.
Sigma xz.
Yeah, sigma xz, you haven't got it that way. You plotted sigma xy and sigma yy.
Yes. So x.
Yeah, it's different. Yeah, it's different. Okay, so okay. That's what I was trying to. I was getting confused with my.
I think it's the coordinate system. Yeah.
But what I was going to say is a really good. Did you calculate the equilibrium equations? If you calculate the residuals to Cauchy equilibrium, you can get an idea of the accuracy of the various methods.
Okay. I think I haven't personally done it, so but I believe Alberto might have done something in those lines.
Okay, but I was going to say that way you could get more confidence that the cut LW2 is more accurate. The residuals were coming out smaller for abacus.
Right.
Gives credence and credibility to it.
Right. Generally, the metric we use is we kind of see the difference in the stresses as we increase the mesh density, and that kind of gives you an idea.
Yeah, I think it's a stronger criterion to do it on the equilibrium because he takes the Cauchy.
Right. Yeah, I understand. Yes, of course.
Okay, it's just it's a small point, that's all. It's not to detract from the work in any way whatsoever. Okay, that's quite an amazing result then with the failure index coming out, as you said in your slides. So if we look at 221, that's quite remarkable. You're almost predicting a factor of 2 difference.
Right. Yes. If you look at the linear element, yes, almost an order less.
That's phenomenal. Was there experimental results? I would imagine there must be experimental results here somewhere where you may be able to compare with experiments.
For the stress field by itself?
No, not stress field, no, the failure.
Or the failure? Yes, actually, for the crack band model, what we did, there was an experimental result associated with it. I mean, no, experimental, no. It was purely numerical again.
Right.
Yeah.
Oh no, but I think there may be some experiment. I mean, people have looked at notches and come and pulled them apart. There may be some experimental data there, which I personally think would be very interesting to compare. Because if you can explain previously unexplained results in the literature, that's very valuable.
Right. Yeah. Probably. Yeah. Sure, I'll look into that.
Okay, I'll just carry on. I wanted to do. There were a couple of things. I was just looking I was interested where you compared your different models with experimental data. So
Okay.
I'll just because there's not it's something that can be very difficult to get experimental data There's a lot less in the literature and models, I think.
Right.
I feel like the development of the elastoplastic chapter, which is chapter 3, so I'm just going to that very briefly.
Okay.
I won't ask questions specifically on that. I think the experimental results in chapter 4, you compared with the shear stress, shear strain, and the
Oh,
softening,
yes.
which was good to see. And I work on it's quite interesting. That's with a colleague of mine at Limerick actually did that work.
Oh, yes, yeah, Huggins.
It is O'Higgins, yeah, no, he's a friend of his colleague and a friend. It's pleasing to see that. I'm on, where should we go? I'm just going through the thesis. If I look at chapter 4.8, figure 4.8, all right. 4.8. You're now looking at your sort of RVs. You've got your fibers and matrix, and you're comparing results and stresses.
Right.
Abacus, and obviously you get a lot less degrees of freedom.
Right.
And I was just thinking, if I look at 4.8 for the sigma 2,
Right.
The fields are remarkably similar, but the numerical values are not so good, actually, not as good as I got from what you've said. You've got a maximum of 14.92 and 14.22.
Right.
So you're looking at a 4% difference in the max. And the minimum is a much bigger difference, 4.58 and 1.76. So, I think that's isn't that a concern? I don't think that's that accurate at that point, is it? Between the sigma 2. What do you think?
I mean, something which we could do more in those lines would be trying to refine both the models and see how it goes, essentially. Here again, for the Abacus 3D model, what we did was, we started from a very coarse configuration, kind of kept increasing the mesh density until it kind of matched well with the COOF results. So we kind of, had a COOF mesh and then started from a coarse Abacus model.
Right, okay. So which do you think is more accurate at this one, the COOF or the Abacus?
I would like to believe it's COOF, let's say.
Could we actually say that you would expect higher, higher stresses, greater stresses for a more accurate model?
Also the fact that if you look at the two fibers below, it's kind of quite close, so getting quite good mesh density there is also a problem, let's say.
Show me which figure I should be looking at there, please.
No, in both the cases, you see the red part you see there, it's kind of it's quite skewed structure as such. So to get the mesh density there is quite, not easy.
Okay. All right, then I was then going to go more onto the multi-scale work and actually just ask about the exchange of information that you're to go through between the macro and the micro at a Gauss point. So you're doing it in a concurrent way, and you're taking. I'm trying. Well, you tell me what you were doing at that point, and I'll see if I understand it fully.
You can give me the page number?
Oh, I haven't got a page number at the moment. It was just actually how you do the multi-scale analysis.
So essentially the idea is at every macro Gauss point I get the macro strain based on the displacement. I kind of apply that via a periodic boundary condition to the micro model.
So this was going to say, so you use a uniform strain across?
No. I convert the 6 non-zero strains into periodic displacements, let's say. So the displacement in the x direction is a function of x, x, y, and z, similarly with other cases. And then I pull it back by averaging the stresses.
Right, so would I be right to say this is displacement control or not? I mean, the reality of structure wants to minimize its energy subject to continuity of displacements and equilibrium conditions, doesn't it?
Right. So here the analysis I've done is all displacement based, if I'm not wrong.
So the load or the stresses get redistributed according to the displacement field that's imposed. Is that correct?
Right. In the micro model, it's based on the strain, which is essentially based on the displacement. Yes.
Okay. Now, if you look at, if you just, I mean, the way you're doing it, I mean, I really like the approach with the multi-scale going from fibers and matrix up to stiffened wing structures, essentially, or bigger. But, I mean, if you look at most structures on the static loading, you can argue that the components within are under displacement or strain control.
Right.
And that load follows, the internal load gets redistributed according to stiffness.
Right.
But then if you look at this approach, what do you think about for impact when you have accelerations? Is that...
I think...
Yeah, you show some very evocative pictures, very informative pictures of stressways in your final chapter, which are with reflections, which is really interesting.
Right, I think it's also something we've been discussing here to how to account for strain rate effects. So it's also, I mean, to put that into the multi-scale model is something which needs, I think, much more deeper understanding for ourselves, let's say. We haven't really looked into it, but we know strain rate effect is something which we have to be careful when we are trying to go into impact domains.
Okay, well, I think that's a very good comment, actually. I think that's good insight from you. I just say as an upper bound, as a bound, you might think that it will be under more load control when you're on a highly dynamic problem, as opposed to displacement control.
Yeah, I mean, it's going to be contact, so of course the contact force is in a sense it's, how do you say, load controlled? If you look at the contacting body perspective.
Yeah, I mean, in reality, the structure minimizes energy, but we use displacement control as an ideal, and that's a bounding argument, and certain load control can be for highly dynamic cases, I think, when you've got high accelerations. At least that's when you've got high accelerations, and the load follows mass and not stiffness. So that's the sort of physical interpretation that happens there. I think that's it from me. I really enjoyed your thesis. Thanks for the in-depth technical discussion. Sorry for the rest of the audience if you got a bit too in-depth, but I think that's one of the opportunities we have in the Bible.
Thank you. And sorry about your flight. So.
Yeah, well, I was going to be in Amsterdam tomorrow anyway because I've got business there, so I've just got another day in Amsterdam, so I'm actually in my hotel room already now.
Cool. Glad it worked out.
But I'm sorry I won't be there to celebrate with the team this evening. I wish you all the best.
Thank you.
I'll stay on in case there's any of the business and any more questions. But that's it for me for the moment.
Perfect. Thank you.
Congratulations again, Ibrahim.
Thank you. Thank you.
Thank you. I invite Professor Giunta. It's your time.
Thank you. So first of all, I would like to congratulate you
Thank you.
and also the other Fulcom students in official framework for the amazing job you did all. There's material for each one than more than a PhD, and also to the person who dedicated time and passion to achieve this great result. So very, very outstanding job.
Thank you.
Then, the nature of my question cannot be in suggesting something because of the first axiom of Kuf. So if you want to suggest an extension of Kuf, there are already someone in Professor Carrera group that is working on it. So my idea is, for example, collaborating. I saw the presentation of Alberto this morning related to the question of Professor about the stress-free condition. For example, if you use a mixed approach, you will get it exactly the stressful. If you use a displacement-free, a displacement-based model, you do what you can. That is decent, very good, but in that case, so what do you think in extending what you did, collaborating with them, in, for example, mixed formulation or HL? If you can see some benefit, it can be easily done. And,
yeah, I think with HL is something we are planning right now to trying to use and trying to compare with LE and HLE how good it works. And probably with mixed model, integrating nonlinear material models has, I think, probably it's not straightforward as you have it, because essentially sigma is a function of strain when it comes to nonlinear modeling, but here it's implicitly in the solution you're trying to solve. So probably there is some accounting you have to take into account.
I was surprised that you, of course, that you use parallel computing, and we are able to mix OpenMP and MPI.
Right.
Did you start from zero? You use some.
So first version of the multi-scale code we developed, one Gauss point ran for almost half a day. So then we are like, okay, so like what Professor said, so we build it from scratch here.
And how many code did you use?
For the problems we just put on the thesis, I think one was with 20 codes each, and the other one was with 60.
Okay.
So
And did you program before?
yes,
Okay. Do you know that there's core arrays now?
yeah, I
Okay.
probably heard of this. Yeah. But then the problem is the way we assemble here is also a little different from arrays, so it could be that too.
No, just for fun.
Yeah, of course, yes, I've heard of it.
It's something. What is it about the question of the Professor you on the homogenization? Notice that the computing time was a little bit high compared to maybe you can when you do homogenization you can already store the stiffness metric and the factorize stiffness
Right.
metrics.
I mean,
Do you do this? or
yes,
not?
right now what we do is when you homogenize, you give, instead of one RHS, you give 6 RHS. So you just invert the stiffness matrix once and you get all the, how do you say, displacement for 6 conditions
For
for
homogenization.
homogenization. And you could use the same data also
Because,
for
yeah,
dehomogenization.
The matrix is already accelerated
Right.
factorized.
Yeah.
You don't need to do the job. So maybe it can be the source of your computation.
Yeah, but I think one part where we are missing is once you get the solution, you also have to dehomogenize local fields in
Local
the
fields.
micro.
Okay.
So that also you have to loop through every Gauss point in
Okay.
the micro too. So computationally even that is, I mean, for a small RDE, of course it's microseconds, but if you look at the randomly distributed RDE, we
Of
have
course.
90,000,
you
yeah, so it takes time.
Okay, perfect.
Thank
No
you.
question and congratulations.
Thank you.
So first of all, again, congratulations for the widespread know-how that you had to acquire to implement all of the things you showed in your thesis. If I can have back your thesis.
Sorry. Thank you for bringing it.
I took some notes on the first page.
Yeah, sure.
The first is again a curiosity about the failure criterion. We know that with CUF you are able to calculate the stress field in very accurate manner. So you have the right stress field. Imagine also using mixed elements, so you have the exact stress field, and you solve the first part of the problem. Second part is put this exact stress field into a failure criterion. So the point now is which is the best failure criterion? And I saw that you used for failure initiation hashing,
Right.
which is very good, three-dimensional one. Just to know, what do you think about lag 5 or others? Did you make an assessment before implementing the hashing, or was it a choice driven by implementation reasons?
I would say implementation-wise, writing a failure index is quite straightforward because in the end it's an equation which is a function of the 6 stresses you have. Probably log 5 has much more terms than hashing and much more forms of damage. So I think in the end, almost all these failure index in somehow is trying to cope with the data what you get from experiment, especially with log 5 you have way too much data coming from experiment trying to fit it. So we haven't done any assessment as such, but if you look at the probably let's say fidelity of these failure index, probably LARC is better. But also one other way we thought we could do was to evaluate failure index at the local scale, like do the homogenization and see there you don't need these quadratic criteria. So you can essentially say, okay, my fiber is breaking because all the fiber has this stress or my matrix starts to crack. So probably I think moving towards that way of evaluating failure index might be helpful than trying to build these large equations with trying to, how do you say, put interactions in between stresses. So I think one suggestion from mine, at least something which I thought of, was to evaluate failure index using multi-scale at the lower scale and tell the upper scale, okay, it's going to crack. And there your index would be purely based on your constituent rather than the mixture of
Yeah. Okay. Thank you. Another question, I think is on slide number 25. Yes, just to have your feeling about this difference here.
Right.
Why do you think?
So if you look at the crack propagation, the first instance is the crack propagating here, and then that corresponds to this drop. So at least our assumption is the fact that the stress field around the initial crack, 3D film, is not good enough. So essentially I just have a crack here, and if I mean we haven't tested this, that's the hypothesis. So if I look at the stress field around this from the initial crack, the stress is not matured enough to propagate. So the 3D film element, it kind of stagnates, and when it reaches this point, actually it has enough stress to continue the propagation, let's say. So that's why you see that increment.
This is very interesting in order not to overestimate with 3D
Right, yeah.
the phenomenon.
Right. And as you see, in a lot of ways, 3D film do overestimate the, like with the failure index.
A very relevant outcome of your work is
Right.
Be careful with 3D.
3D and
And if you came back again, slide 25, back to the previous picture.
this one, no?
There was another similar, maybe later.
Okay, here maybe.
Yes.
Yeah.
Here we see kind of sudden cracking, three major events.
Yes.
Again, what do you think about that? We see that they are different. We don't have exact experimental result.
Right.
So, okay, it's just speculation, but which is your feeling about these three big events? Is again due to the very accurate stress field recovery.
Right. I think even if you look at the reference I put here, like this paper, they also say it's a very brittle like. Their experimental investigation shows very similar. I mean, not exactly the same way, but brittle like behavior. So I think probably it's to the fact that because in the end, the mesh convergence again almost always done based on just elastic analysis. We never do mesh convergence by putting a crack there and seeing whether the stress fields are still good enough. So that's something also we could investigate and see, okay, this is your input, this crack state is your input, and try to make sure the stress fields are converged. Probably that could give us a better idea.
Okay, now all the other questions have been already answered by your previous answers. So, thank you very much.
I have only curiosity on your viewpoint number 45.
This one?
Yeah. Yeah, exactly. The right chart. I was impressed also when I was reading the thesis that there are three different models which more or less converge on the same result. And in this picture, it seems that the experimental test is different. Well, what's your feeling about this? There are 20 years from the experiment,
Yes.
more or less.
Yeah, I think also one thing which is common in all these three models is it's arc-length based model. So you see this kind of how do you say snapback, what you see here, and the experiment was done with displacement based control. So I don't know whether that falls because that is quite evident here. You see the curve sudden drop from this to this because you're in displacement control. You're not capturing this curve. I mean you're not supposed to capture the curve. It's not physical, right? So it's displacement based. probably. And also one thing which I saw also is you see the deviation here is due to the fact that the propagation gets closer to the boundary. So the length which these two people use are different too. So I think this part of solution can also be dependent on how close your propagation is getting towards the boundary.
Yeah, what I was trying to express that probably with this great improvement of the medical modeling, probably the test case should be redesigned and re-executed because it's much more detailed in terms of comparison and benchmark.
And also they give us the data for the data measurement, the energy and the stress, and I think those could be co-fitted to the original less fidelity model you have. So yes, that's true.
Okay, I think it's time to close if there are some questions. No. Okay, thank you and congratulations.